Hi, everybody. I'd love to introduce Mathieu Bauchy from UCLA, and he's been working on making concrete more sustainable and green using machine learning methods. Welcome, Mathieu.
Thank you. Yeah, so glad to be here. I'd like to tell you a little bit about like I would say our journey in concrete. Tell you a little bit more about concrete as well, because it's people don't always realize the importance of concrete in the world and the carbon contribution that it has. So so let me jump straight through it. So like the thing about concrete is that it's actually hard to think of a more defining materials that really defines who we are. We know we use concrete to build our house. Concrete is how we travel from places. So it's, to some extent, it might be the most the material that defines the best human civilization, and it has enabled so many things. It's really hard to think of a world without concrete, maybe much more than any other materials. And clearly, concrete is not the most high-tech material that there is, but the scale, like there is really no other materials that has this scale. And so I'm showing you the number here. Like every year, we produce 4 tons of concrete per person on Earth, and so that's by far concrete is the most used material. It's actually only second to water, right? There is really no other material that is as much used as concrete in the world. And the thing with concrete is that because we produce so much of it, then it comes with a cost. It comes with the cost of like a very significant CO2 emissions. And again, it's not so much that concrete on its own is like very carbon intensive, but it's more about the scale of how much concrete we produce. And so this is really what we have been trying to do, is to see how we can use new developments in AI, in machine learning to tackle this project and to try to reduce this carbon footprint of concrete. So I'd like to tell you a little bit more about so what's the problem that we are trying to solve, so the carbon footprint of concrete, and then I'll show you like how we have been using machine learning and AI to try to reduce carbon's footprint. And so when we think about the carbon emission due to concrete, it corresponds to 8%, roughly 8% of the global CO2 emissions. And so that doesn't seem like a lot on its own, but when you compare with all the emissions from aviation is only 2%, right? So it's 4 times. Like concrete alone is responsible for 4 times more emission than all the aviation industry. So it's really a significant contribution. It's much more than any other materials. So there's really an urgent need. And the problem is that, like all other industries, they are decarbonizing, transport, there is electric cars. You have like everything related to energy, like we are transitioning to either nuclear power or like green power, but concrete is very hard. It's a heavy industry. There is some thermodynamical limitation regarding what you can do to decarbonize concrete. So those heavy industry like concrete, steel, glasses, those are to some extent the hardest to decarbonize. And so when you think about the carbon footprint of concrete, there is really like different contribution from the very beginning of its production to the very end of the life cycle of an infrastructure. So when you look at that, if you want an accurate description of the embodied CO2 associated to concrete, like you need to take all of this into account. Like you need to take what we call the A1 contribution. This is the emissions due to the raw materials like cement, the aggregates, like all the raw materials that goes into concrete. Each of them has an associated A1 contribution due to their manufacturing. Then you have the A2, which is the transport. So we need to transport those materials like cement up to the concrete plant. And then there is the manufacturing of concrete itself. So those are, for example, the energy consumption of the concrete plant itself. Then after that, once concrete is made at the plant, we need to deliver it to the job site. So that's the A4, etc. And then so you have everything related to the to the use of the infrastructure, any repair, any maintenance, etc. Like all of this goes into the overall carbon contribution of concrete. And then everything related to the end of life, so the decommission, the recycling, all of this. So what I'm really interested in is really the beginning, so what we call the cradle to gate. So that's what I'm going to talk about today. Anything related to the production of concrete itself, but not so much what happens after that. Like that's a whole new different problem, very very different problem. More about the structure and the buildings and things like that. So what I would like to talk about is how do we reduce really the depth. Every time we build something new, we start with a depth, which is the energy that was, or the emission that were due to the production of the concrete itself. And then, you know, we can do many things, like whether it's a building, a data center, things like that. We can do many things to try to save some energy during the life of the infrastructure itself, but we can never recover this initial depth about the concrete production itself. So that's really what I would like to focus on during this presentation, is how do we reduce as much as possible this initial depth? And this is, for example, something that's very important for any company that has any kind of carbon neutrality goal. Like those are carbon contribution that you can't avoid, right? We can't. There is no other material than concrete that you can use for most infrastructure. So all of those emissions due to concrete manufacturing, they will need to be offset. And so those are some expensive carbon offset that you need to buy. So that's what I would like to focus on today. So then
question,
yes.
What fraction of the overall emissions are these stages?
Yeah, I mean, it's like the thing is that those initial emissions, to some extent, those are the ones that are the best quantified, because there is a clear methodology to quantify those carbon emissions due to concrete manufacturing itself. So A1, A2, A3, everything related to A4 and A5, so the transport. So that would be like purely the transport in the concrete truck. So like fairly small contribution as compared to the cradle to gate. The problem with everything related to B and C, it's very hard to quantify, right? You need some life cycle analysis. It's hard to estimate what will be the lifetime of the infrastructure that you build. So it's hard to give a good answer regarding that. Like the thing is that everything regarding B and C, those are, there's already some good solutions, you know, like higher thermal efficiency, maybe using like alternative solar energy or renewable energy, things like that. So there's already some efforts to try to reduce the service life, the emission associated to the service life of the infrastructure itself. But like it's still really the production itself that remains the hardest to decarbonize, because you can't use any renewable energy for that. So yeah, I don't have a good answer about the fraction it is, but it is significant for sure. It's certainly a decent fraction, like probably more than 50% if I was to guess.
Thank you.
So yeah, so again, so there is a clear methodology, at least from A1 to A3, and this is what is governed by the concrete PCR that gives the methodology on how to calculate the environmental impact. And so usually, at least for producers that have embraced this type of approach, you can report the carbon emission of concrete with an environmental product declaration, so like an EPD, which is what I'm showing on the right. So it's something that really looks like the nutrition information of food, except that it summarizes the impact of material, or in this case concrete, on global warming potential, and some other type of impact as well, like ozone depletion potential, acidification potential, things like that. So global warming potential is just one of the negative aspects associated to concrete production. That's the one I'm going to focus on, but there is other ways, like other types of hidden costs that that concrete production has. And so at the end, what you get is really a number that is the global warming potential that is quantified in terms of a CO2 equivalent, and it's reported per cubic meter of produced concrete. So it's really what quantifies what was the contribution of producing 1 cubic meter of concrete. And so here, for example, I'm showing one example of the global warming potential of a given concrete with a certain types of strength. And so when you look at the breakdown of the A1, A2, and A3 contribution, so it's really the A1 contribution, so the production of the raw materials themselves, that has the major contribution. So that means producing cement, producing aggregates, producing the chemical additives that are used in concrete. That's really what corresponds to the biggest fraction of the global warming potential of concrete. So those are the constituents that typically goes into concrete. So concrete, you know, is something that you make by mixing sand, aggregates, water, cement, and some chemical additives. So you mix all of this together, and initially you get some kind of a slurry, a gray slurry that you can use to build things, and eventually this is going to turn into a stone. So it builds strength over time. So that's the beauty of concrete. It's like again, it's a very low-tech material, but when you think about it, like concrete is very magical, right? It's something that is workable initially, so that you can make it have any shape you want, and it builds strength on its own over time, just by a chemical reaction between water, sand, between water, cement, and all the cementitious material that you have into concrete. So, and it's gradually going to build strength on its own, right? So it's again, like a very interesting material that is dynamically changing over time. It's really a living material, and so this is also something that makes it complex to predict the behavior of concrete, because it's something that is not really something that's constantly evolving over time, over the years. Like even years after you have built a given concrete, it's continuing to chemically react. It's also reacting with the atmosphere. It's getting carbonated over time, etc. So this is a very complex material, and that's why, even though it's the most produced material on Earth, it still remains hard to really predict its performance over time, and that's what makes it hard to also decarbonize things, because we don't even know how to reliably predict how a given concrete is going to perform over time. So when it comes to concrete, the prime of concrete is really about cement. So cement is one of the ingredients of concrete. And so when you look in terms of by mass, cement is actually just a small contribution, right? It's 15% of concrete by mass. But when you look at either in terms of cost, or even worse in terms of carbon footprint, cement is really the main contribution to concrete's cost. So it's 50% of the cost, and it's about 95% of the carbon footprint of concrete. So when it comes to reducing the carbon footprint of concrete, what we really mean by that is, can we reduce the use of cement in concrete? Because that's really anything else that you put in concrete, of course, will have its own carbon contribution, but it's fairly minor as compared to that of cement. So cement obviously is very important in concrete. That's what reacts with water, and that's what gives the strength to concrete. But the more we can reduce the use of cement in concrete, the more it's going to decrease its carbon footprint. So this is really what we are trying to do. Like, how can we use less cement in concrete while still, we still need to keep the same strength and everything, right? Like, we can't compromise on that. Like, if we decrease the strength of concrete, that can have some serious safety consequences. So when it comes to concrete, we can't make any compromise on the quality, but we still are exploring ways on how can we still use the same concrete using the same strength, the same safety, but using less cement, and hence lower the carbon emission associated to concrete.
So, question.
Yes.
Can you contrast? So, there's are low carbon concretes. So, is there like a different kind of cement as opposed to less cement?
Yeah, so there is really, many approaches that people have been doing. So I would say the easiest one is to try to reduce the amount of cement in concrete. And so that can be done in different ways. That can be done by optimizing the concrete itself. So like, for example, optimizing the fraction of the different aggregates. It can be done by using some chemical additives that can increase the strength of concrete so that you can use less cement in return. Usually the most common approach is to try to replace cement by some what we call some alternative supplementary cementitious materials. So that can be fly ash, slag. So those are typically some waste byproduct. For example, fly ash is a byproduct of coal energy production. Slag is typically from steel production. So those are some pretty efficient way to reduce the use of cement in concrete. The problem is that we are we're not really using coal as much as we used to. So the amount of fly ash available in the US and in the world is decreasing over time. So this is starting to become harder and harder to find those materials that can replace cement in concrete. And then you have like completely different approach, like for example, designing a new type of cement, like a brand new type of cement, things like that. So there is really many different approaches. The problem with concrete is really the scale, right? Like we are producing so much of it that there is not that many materials that can meet this scale. Like if we come up with a new way to produce cement, like can we really build several tons of these materials per people on Earth per year? Like when you think about the types of materials that we produce, like nothing really has the scale that to replace concrete. And so that's what makes it very difficult. So that there's many of those approaches, but in terms of the scales, so far, like the only approach again has been to use slag or fly ash, because there is some large quantity of those. But even those, we are starting to run out of good quality fly ash, things like that. So yeah, that's clearly a challenge, and that's why we think machine learning can help in that regard.
Makes sense. Thank you.
So yeah, so when it comes to decreasing the amount of cement in concrete, like the way we do that is by designing new concrete formulation. And so making concrete is like making a cake, in the sense like you mix some ingredients with different fractions, and depending on the ingredients that you use and depending on the fraction, the quantity of each of those ingredients, concrete will have different properties. And so when it comes to reducing the amount of cement in concrete and reducing the carbon footprint of concrete, we really need to optimize the recipe of concrete. So the recipe on how we make this concrete cake. And so this is really what concrete design is about. It's about how do we optimize the fraction of each of the constituents of concrete to achieve the attributes that we want for concrete in the most economical fashion, or with the lowest carbon potential. So like when we design a concrete, usually, so that we have certain attributes in mind. So those are the attributes of the concrete product itself. And so for concrete, usually you want to have a certain strength. That's the strength that you need to carry some load, for whether it's for a bridge, for a wall, or anything like that. And then you have certain types of durability requirements, like to make sure that the performance of concrete will be maintained over time. So this is typically what the consumer cares about. But then there is all kind of manufacturing attributes ourselves, and that's the case for any materials, right? Like it's not just about the property that the customer cares about. It's also like, can it actually be made, and how easy is it to make it? And so In the case of concrete, there's really several factors like the slump. The slump characterizes like how fluid concrete initially is. So to build something, you need concrete to be initially like a liquid slurry that you can use to adjust the shape of the concrete. So that's dictated by the slump. So that's another factor. It's not just about strength. There is like the slump, the setting time. Setting time dictates how long it takes for concrete to turn into a solid stone. There is, most of the concrete is usually pumped, and so we need to make sure it can be pumped through a given pipe. So what I mean by that is that, designing a new type of concrete that would be greener, it's not just about ensuring that it has the right strength. Like there is many requirements to make sure it can be used in practice. So if you think about this mathematically, it's a multi-objective optimization or multi-constraints optimization. There is many things to ensure to make sure it can be used in practice. So so this is really what can be formulated as a mathematical optimization, in the sense that you have a cost function. This is what you want to reduce. So in this case, we want to reduce the global warming potential of concrete. And then you have some degrees of freedom that you can adjust. In the case of concrete, we can adjust the constituents of the concrete, and we can adjust the quantities of each of those constituents. So those are the degrees of freedom that you can have. And then we have certain constraints. So it's really an optimization under constraints. So the strength needs to meet a minimum level. We need to ensure that the slump of concrete is within a certain range. So there's a whole types of constraints that are usually constraints dictated by either the application of concrete, right? So depending on what you build, whether it's for foundation, for walls, or slabs on grades, etc., like each types of concrete will have a given strength target. So it's not a unique optimization, like it has to be done application by application. But yes, so it's you can formulate that as a mathematical optimization where you're trying to reduce a certain cost function by adjusting some degrees of freedom while ensuring that a certain numbers of constraints are met. So when it comes to the degrees of freedom of concrete, again, it's really about adjusting the constituents. So what I'm trying to talk about today is really like, I would say, a very pragmatic approach of what can we do today with the materials that we have in concrete, and without changing fundamentally the way concrete is made. So when we discussed earlier about all the different approach to make green concrete, like there is really many different ways, including like designing some brand new types of cement, things like that, or maybe designing some concrete that do not rely on cement at all. But so those are things that still probably require about 10 to 20 years of development. So what I'm interested is what can we do now with the materials that we have, that the producers have at their plants. What can we do to make the production more efficient without waiting for a few decades to get a new type of cement or something like that? And so like a very simple pragmatic way to do this is just let's use the materials that we have already, and let's see if there is some room to optimize concrete by just slightly adjusting the fraction of each of those constituents. So each of those constituents, like cement, chemical admixture, aggregates, sand, can we, by simply changing the fraction of those constituents, can we reduce the amount of cement, make the concrete less carbon intensive, and still keeping the same strength? So that's really what I'm trying to discuss today. And again, like a very clear opportunity in that regard is that cement can be replaced by some other alternative materials. So typically fly ash, slag, or silica fume. So like those materials have been shown to be efficient in replacing cement, but it's every time you replace cement by one of those materials, it's going to impact the strength of concrete. Those materials might not be already they might not be available everywhere, and they might not be cost efficient, right? So it really depends on the location in the US. Some locations have access to cheap fly ash when they are close to a coal power plant. In California, unfortunately, we don't really have that. So like fly ash, slag, those are all very expensive materials. This is really, we can't do that at the national scale. It needs to be done really, state by state, and probably even like plant by plant, because the materials that are available and the price of those materials and the transport of those materials are going to be very dependent on where the concrete is being produced.
A question. So
Yeah.
does Portland cement, is that generally available?
Yeah, so I mean, it's available. The only question is how far does it need to be transported, right? So and how is it transported? So we have some cement plants in the US at various locations. So it is available, and cement is you produce this with limestone and with clay. So it's those are materials that are very widely available. So there is no risk of really running out of cement anytime soon, and that's really why cement is so hard to replace to begin with. It's really made of very cheap and largely available materials. So it is available. The only question is, depending on where the concrete plant is located, you will need to either import cement either with a barge if you have access to a river, or by road if not. So this is going to have an impact on the A2 contribution to the global warming potential, which is the transport. But this is still small as compared to the cost, the carbon footprint of producing cement itself. And when you look at the way you produce cement, like there's really not much you can do, because the way you produce cement is you start from limestone, so CaCO3, and you heat it to form some clinker. And when you do that, the CO2 part of limestone is going to be basically released into the atmosphere. So there is really not much you can do to decarbonize the production of cement itself. It's really a chemical reaction of turning CaCO3 into just CaO plus CO2, right? So it's there is really not much you can do to avoid those carbon emissions due to the production of cement.
So is on-site carbon capture an option, or is it to diffuse a gas there?
I mean, it's an option, but it's just the thing with the problem with concrete, it's so cheap that everything that you do. So if you do a carbon capture, the cost of capturing the CO2 will probably be almost the same as the cost of the concrete itself. So it's probably going to be even more than the concrete itself, right? Like, so for every ton of cement that you produce, you typically release about 0.8 ton of CO2. So the cost of capturing this CO2 would pretty much like multiply by 2 or 3 the cost of concrete. So it's not something that is really a viable option, and that's really the problem with concrete, is that it's so cheap that there is really nothing that can be economically viable as an alternative to concrete.
Got it. Thank you.
So the question is, so let's say you want to design a new concrete. So you need to figure out how to mix those materials together with certain quantities, and so that's really like a typical optimization problem. And so the question is, can it be solved by brute force? And so for this, like, you can try to estimate like how many solution can be considered when you design a new concrete. And of course, the number of solution is virtually infinite, because you can mix those materials in an infinite number of possible ways. It's a continuous problem. But if you're trying to estimate like the number of possible concrete formulations that can be made, so this is like a fairly conservative estimation here, by considering that you have access to only one cement, one fly ash, one slag, one type of sand, one type of sown, and one type of plasticizer. And so if you really think about like what's the minimum and the maximum amount of those materials, and what could be a typical increment that you might want to consider. So if you do that, then basically you get about like more than 13 billion possible solution to that. So basically, even though concrete is it's just mixing a few materials together, like the number of solution to this optimization problem is very large. At least it's large enough that you can't really solve that in a brute force fashion. So and the premise that this is just for one optimization, but when you look at a given producer, typically in their plants they will have about like several hundreds of different concrete that they would mix, and this is due to the fact that there is not like a single concrete formulation that can do everything. Like concrete has many different applications, whether it's to build wall, foundation, things like that. So every concrete formulation has a distinct set of performance that it needs to achieve, distinct constraints, distinct requirements, things like that. So there is several hundreds of concrete formulation that every plant would have. And so you need to do this optimization like many times, and for each plant, right? So it's a complex problem if you want to do it at scale. So that's why we think that machine learning can help in that regard, due to the fact that it can be used in a high throughput fashion to solve this kind of problems. Okay, so let me talk about. Oh yes, sure.
Do you have the ability to simulate the outcomes of these samples, or is it more like physical experiments are required?
Mm-hmm. Yeah, so I mean, of course, that's what we want to do with machine learning, but there is no otherwise. There is no chemical or physical model that allows you to predict what the performance of a given concrete would be, right? So you can't really simulate that like you would with typical materials. There's really three main difficulties: the fact that concrete is a material that is constantly evolving over time. So it's a complex chemical reaction that occurs between the cement and the water, and continuously change over time. There's the fact that concrete is very multi-scale material. So you have what's happening at the atomic scale, but then there is a mesoscale, like microstructure, and then there is several different scales in concrete, and each of those scales is going to have an impact. So at each of those scales, there are some modeling tools. Like, at the atomic scale, you can do some molecular dynamics. You can have some continuums like FEM to model what happens at the continuum scales, things like that. So each of those scales can be modeled, but when you consider concrete as a whole, it's very complex to model that all together. Yes, so this is really what the fact that concrete is multi-scale and is very largely heterogeneous. You can't model it like the way you would model like a semiconductor or anything like that. So basically there is no good chemical or physical simulation methods to predict the performance of concrete, and of course that makes it ideal for machine learning to just learn this in a purely data-driven fashion without any kind of chemical or physical knowledge of the underlying mechanism.
Okay, makes sense. Thank you.
Okay, so of course, machine learning has been used for many materials already, like to predict their performance, discover new materials, but there are some unique challenges when it comes to using machine learning for concrete, and that's what I'd like to talk about in the coming slides. See how we have addressed those challenges to the specific case of concrete. And the first thing about concrete is really about availability of data. Of course, that's very critical for machine learning. And when you look at what's publicly available, there is a few data sets, but it's typically just about 1,000 data points. So it's very little data available. Even though concrete is the most used material on Earth, there's not so much data available. So that's a challenge. Concrete is a material that is very variable. Like when you make a concrete and test its strength, for example, you're going to get a different answer every time. So, and it's very prone to error. So typically when you work with data sets involving concrete, there's going to be like many outliers. So that's something we need to take into account very explicitly. One thing, it's not just related to concrete, but just for materials in general, is that we don't want to just interpolate, develop some models that can interpolate performance for concrete. We want to design some new concrete that don't exist yet. So we really need to extrapolate to make some prediction about some new materials, new concrete that don't exist yet. And of course, machine learning is typically notoriously bad at extrapolating outside the training set that it was used to build a machine learning model. So we need to take some extra precaution into making sure that as much as possible we have some models that can extrapolate to a certain degree outside the domain that the model was trained on. And then something that's very important for concrete is we need to be aware of the uncertainty of the prediction. Like when you build concrete, what matters is the strength that you're going to get, but also the uncertainty of this strength, and that's something that is explicitly taken into account in the concrete, like in the building code, for example. So we always need to be extremely aware of the uncertainty of the prediction. So I'd like to show you some things about how we addressed each of those challenges individually. And the first step, of course, was to create a database to build those machine learning models. So that's something we collaborated with several concrete producers to build what we think is the largest database of concrete properties in the world. So at this point, we have about 1 million data points of concrete. When I say data points, it's for each data points we have the concrete formulation. So what were the constituents that were used, and the quantity of each of those constituents, and we have the associated performance. So we have the strength, we have the slump, so all the typical properties that are typically used to specify a given concrete. So here what I'm showing is just some visualization of this database. So we can see some obvious trends. Like for example, here I'm plotting the strength of concrete as function of the ratio between the water and the cementitious materials. So the more water you have in the concrete, the lower the strength becomes. So that's one of the trends that we expect. It's kind of the opposite when you plot it as a function of how much cement you have. The more cement you have, the higher the strength becomes, right? So when you look at those trends, I mean, you see some obvious trends, but there is really nothing that would really allow you to build like any kind of linear models or anything like that. Like it's you really need machine learning if you want to isolate the contribution of each of the features of concrete into predicting strength, slump, and things like that. So then the formulation of concrete is one thing that matters, but there is also, it's at the same time a physical and a chemical problems. And the exact chemistry of the cement that you use in concrete also matters. So when we want to make some prediction about the strength that a certain concrete will have, it's not enough to know how much cement you are using. We need to know the exact chemical composition of the cement. So that's what also makes concrete a very difficult material to work with, is that it's at the same time the physical characteristics and also the chemical characteristics of the materials that matters. So we have like a second database that we use that contains like several thousands of cement with different chemical compositions. And that's what we use to infer the role of the chemistry of the cement into the performance of concrete. And then we need to also have this for any other kind of material that we use to replace cement with. So for example, fly ash is typically the main material that cement is replaced with. So we have the same types of information here, where we have accumulated about 20,000 different data points for a fly ash of different compositions. So fly ash is typically like a calcium aluminosilicate materials. So depending on the fraction of calcium, silica, and alumina that you have in fly ash, it's going to have different types of reactivity. It's going to impact the strength of concrete in different ways. So again, we need to explicitly take this into account when we predict the performance of concrete, because fly ash is very heterogeneous. The properties of fly ash can change a lot from one plant to another, and it can change over time. So we need that level of details to really be able to make some prediction. So that's the first thing. So getting some data. But now that you have the data, like data involving concrete, it's one of the the noisiest data that you can work with. So we need some robust way to deal with outliers in those types of data sets. And so there's many different ways, many reasons for which you may have data, outliers in database, whether it's for concrete or for any kind of database. It can be an experimental error. It can be an error when batching the concrete. So maybe there is an error on the weight of a certain materials. But it can also be an outlier is, an outlier is something that doesn't behave as expected, right? And it can also be that there's a new types of concrete with a specific combination that gives you something unexpected, but that doesn't necessarily mean that it's an error, right? So it's really a challenge when we work with concrete datasets to be able to clean the database, to remove those that are associated to actual errors, whether it's a typo, unit conversion, etc., but also to keep those data points that may not behave as expected, but are actually true behavior, because maybe those are the ones we care the most. Like if we really want to find a new type of concrete that has a much lower carbon footprint, but still a high strength, maybe this is going to initially appear as an outlier. So we can't just remove everything that doesn't appear to behave as expected. So we spend quite a bit of effort on developing some tools to identify outliers. And so that's one approach that we have been using here. I won't go into too much detail, but basically the main idea is that there is many different algorithms to detect outliers, and each of them might be good individually. But the approach that we have been using is to rely on an ensemble of outlier detection algorithm. And so the idea of this approach is that we start with, we build a pool of outlier detection algorithm. So this can be based on, it can be density based by looking at the density of data points. It can be distance based, can be angle based, etc. So we take a pool of, let's say, 20 different types of algorithm to detect outliers. And then we do either a forward or a backward search to find what's the most efficient ensemble of those outlier detection algorithm to maximize the accuracy of the models. So this is really the idea of combining, finding for each specific priority and each specific problem what's the most efficient combination of those outlier detector. And so the way it works is typically we start with the raw data sets, then we add outlier detector one by one. At each step, we find what's the most useful outlier detector algorithm to add. And so what we typically observe is that as you start adding some outlier detection algorithm, the accuracy starts to increase. And then at some point, when you start to remove too many outliers, the accuracy starts to decrease again, because you're starting to remove points that are actually useful for the model to learn the relationship between concrete constituents and concrete's performance. And so basically, that's where we know we have found the optimal combination of outlier detection algorithm. So that's what the approach that we have been using. We call it the ensemble-based outlier detection, so EBOD. And so it has been, at least for the case of concrete, it has been an efficient approach to really find the best balance between cleaning the data sets, but without removing those data points that are actually useful for the model to learn how to make some predictions. Okay, so then there is a distinct issue that's specific to concrete, but also for materials in general, which is that typically we work with distributions that are not uniform. And so that creates some unique difficulties when it comes to using machine learning, because, for example, if you take a typical like cross-validation approach, where you would randomly split your training set into a validation set, when you have those non-uniform distribution, you can have some models that are actually obviously overfitted that will fit the data very well and will give you a very good validation score. But those models would not be good to really predict the performance of new concretes that are not in your data sets already, right? So I think that's a common approach, and we see that in in many publications. Like if you just rely on a random cross-validation, you tend to inflate the performance of your model, but it doesn't really reflect how good the model is at really discovering new materials. So the approach that we are using instead is we're trying to find ways to really have a model that can be used to actually extrapolate and predict the performance of new concrete that would be very different from the one that we have in our training sets. And for this, we need to favor model that can extrapolate outside of the range of the training sets, and that can be reasonably able to generalize outside of the training sets. And so the approach that we have found to be the most efficient for that is to kind of leave one cluster out, or local cross validation. And the idea of this is that the first thing is that we take our data sets and we group them into clusters, clusters of data points that look like each other. So we can use different approach for that, but probably even like a simple k-mean algorithm would work reasonably well for that. Once we have grouped the data points into cluster, what we do is that we, rather than doing a random train validation split, we take all of those clusters one by one, and then we do a cross-validation where we isolate one cluster that's going to become the validation set, and all the other clusters are going to be the training set. And we do that in a cross-validation way by using all of those clusters as a distinct validation set. And then we adjust the hyperparameter of the model to reduce the validation error as much as possible, right? So we still keep the same idea of cross-validation, but we do it cluster by cluster rather than with a random train validation split. And so when we do that, we find that on average, this is going to yield like a much simpler model, and model that tend to be more linear in nature and can extrapolate better outside of the range. Like they are really trained to extrapolate, trained to learn from one cluster and extrapolate to the next cluster. So those types of models tend to be much better to make some reasonable extrapolation outside of the range of the training set that they are trained on. And so, yeah, in general, those models, of course, they are still based on neural networks, so they are not fully linear, but they tend to be more linear. And that's basically because, linear function is kind of the only function that really can extrapolate reasonably well outside the range that is trained on. So again, those models are not they are not linear. They are still like based on neural network, but they tend to give more linear extrapolation. And we found this to be the most efficient to discover new materials that are different from the one in the training set. And then the next thing is, again, we need to have a good way to estimate uncertainty. And uncertainty can come in many ways. It can be like maybe in our database we have like several concretes that are close to each other but with different strength, and in that case we need our model to be aware of that. But there is also, like, whenever we extrapolate, we need to make sure that the more we extrapolate, the uncertainty of the model is going to increase, right? So for this we use an approach that is based on deep ensembles. So rather than training a single model, we train an ensemble of deep learning model, and basically we use that to estimate the uncertainty of every prediction that we make. So then let me show you a little bit of actual results. So here I'm showing the prediction versus true properties. And again, we need to do that for several properties. So strength, shrinkage, slump. So when we look at this, like that gives us an idea of how good the model is. Like we don't expect like really R square equal 0.99 or anything like that, because like in this case, when we are satisfied when the accuracy of the model becomes comparable to the uncertainty of the measurement itself. And when it comes to concrete, if you measure the strength of concrete for the very same concrete, you will get different answers every time. With a typical, for example, the strength of concrete is typically varying with a standard deviation of about 500 psi. So like the way we looked at those models is like we look at the accuracy, for example, the root mean square error, and we look at is the accuracy comparable to the uncertainty of the measurement itself. And so this is typically what we are able to achieve with those models. They do come with a fairly high uncertainty as compared to other types of materials for which you can have more higher level of accuracy. But we do expect that for the case of concrete, because again of the variability of concrete as a material itself, and the fact that those measurements come with a fairly significant error when you just repeat the same experiment several times.
So question, when you say uncertainty, do you mean just leave prediction, just leave leave cluster out cross-validation error, or do you mean more like a Bayesian prior or posterior uncertainty?
So here, like that's like a test set accuracy, right? So we typically have this kind of two layer of when we do this leave one cluster out, we start first, so we take our data set, we group it into clusters, then we isolate certain clusters, and that's what we're going to use as a test set, so the final test set. And then we use the rest, and that's what we do the cross validation on, right? So what I'm showing here is like the test set accuracy of predicting those clusters that were isolated from the very beginning. So it's like a traditional test set, but really in the context of extrapolating to new clusters.
Got it. Thank you.
Let me skip that. Maybe I can come back at the end, but that was an attempt at kind of interpreting the models. But I really want to show you like how we use those models. I mean, predicting concrete performance on its own is great, but what we really want to do is to use it to optimize and discover new concrete formulation. So again, we're coming back to this optimization problem here. We're trying to reduce the carbon footprint of concrete, and for this we can adjust the constituents of the materials that concrete is made of. And so now, of course, we can solve this optimization much more efficiently because we are modeling our cost function in terms of a neural network. So the idea is that now that we have those machine learning models, we use them to solve this optimization problem. And this needs to be done like concrete by concrete. So we start with for each concrete, what is the strength that we need, what is the target slump that we need, what are the materials that we have access to at a given plant, and based on that we solve this optimization problem with the machine learning models that we have for each of the properties. So let me show you an example here of the kind of result that we get. And like I think one way that is interesting to test the accuracy of those approaches is to compare them with what a human would do, right? So here the kind of the test case that we had is we worked with the concrete producers. We went to a certain plant. So it was in the San Jose area, and we asked the local expert, so the local quality control producer, to design a concrete that would have the lowest possible embodied carbon with a certain minimum strength and with a given target slump. And then we asked AI to do the same, basically, and so we compared what the human was able to do with what the AI was able to do. So the very first thing is, so the concrete being produced, did it actually meet the strength that we wanted, right? And so here what I'm showing is 3 results. So the green is the strength of the concrete that was discovered by AI. And in this case, the strength was indeed higher than the requirement of 5,000 PSI in this case. In blue, that's the strength of the concrete made by the human, which, I think that's kind of illustrates one of maybe the weakness of humans, is that when we're trying to optimize, sometimes we can be a little bit greedy, and in this case, like for example, the concrete optimized by the human was actually slightly short on the strength. But when it comes to machine learning, so again, we for each concrete we can predict its strength, but we can also predict the uncertainty of this, right? So we can have those 2 aspects to make sure that when the AI recommend a concrete, not only we predict that this concrete is going to have a given strength that exceeds the target, but we also have the uncertainty of the predictions to make sure that it's going to confidently exceed the target. And that's something that human typically don't have. Humans they have some intuition to predict what the strength of a concrete will have, but not necessarily the uncertainty of this prediction. So that's, to some extent, that's one advantage of machine learning or other humans in that respect. And here I'm also comparing the results with some kind of reference concretes for the National Ready-Mix Association. So those are like some national-wide average that I'm using to compare the results with here. So another aspect of this optimization was to make sure that the concrete that is made is actually workable in practice. So this is what we basically we need to ensure that the slump of concrete is within a certain range. And in this case, each of those 3 concretes were inside that range. So in this case, AI was as good as the human in that regard. But really what was the key result is in terms of the embodied CO2, right? So like this is, in this case, the global warming potential in blue of the concrete that the human found was the most like green concrete that can be made with the materials available at this plant. And actually the one identified by the AI was significantly lower, right? Like about a 35% reduction as compared to the human, right? So this illustrates, like, I think fairly well how AI can be used to, I would say, overcome the bias that humans can have. Like in this case, for example, the way the AI was able to generate this concrete was by using types of aggregates that the human thought would not be possible to use in concrete. And find some combination that we are not initially thought to give the right strength. So, like in this case, AI is very agnostic. It doesn't have any kind of bias. That, of course, it has the bias of the training set that it was trained on, but except that it can really find some patterns that humans would not see, right? So this illustrates like how much we can reduce the CO2 emission of concrete simply by using the materials that we have already and just finding ways to better optimize the fraction of each of the materials that goes into concrete. And one thing that was also interesting is that usually when we think about green concrete, usually we think of something that's more expensive than the concrete we are making today. But in this case, since the goal of this was really to reduce as much as possible the cement in concrete, like reducing cement is also good for the cost, because cement is the most expensive ingredient inside concrete. So it's the concrete mix that was found by the AI was actually more economical than the one found by the human. So in this case, you kind of win on both fronts. It's not only a concrete that's going to be more economical, cheaper, but also with a lower carbon emission. So it's one example here where you have a greener alternative that doesn't come with any cost premium and is actually cheaper than the reference that was used so far. So again, like those are some results that were obtained in California here. So California is a very significant. I mean, it's a very distinct market because there is no cheap flash available. So those results may not replicate in the same fashion in other region in the United States. So we can try to understand, of course, it's hard to understand sometimes what the AI recommends and why it recommends that instead of another formulation. But what we can do is we use some SHAP analysis here to try to interpret the reasons of why AI recommended like a new concrete formulations. And the way we do that is that we decompose, we look at the concrete that was suggested by the human, then we compare it with the concrete suggested by the AI, then we look at each difference one by one, like for each of the input, what's the difference between those two concrete, and then we can isolate using the machine learning model and using a SHAP analysis, we can isolate what was the contribution of changing each of those input one by one. How did it affect the strength? How did this affect the cost and the carbon emission? So that gives us a way to try to interpret what the AI did, even though in practice it's more like a black box. And sometimes it gives some answer that it's very hard to understand like why it came out to those answers. But at least those tools gives us a way to try to get some intuitions about why a certain concrete was predicted. I'm going to skip that and just show you some final result if we still have a few minutes about how do we do this at scale, because so far I showed you like one result for one producer at one plant for one mix, but if we really want to have an impact, we need to do this at a much larger scale, right? And so when it comes to really going from a pure laboratory scale optimization to something that can be really at a much larger scale, like there is a certain number of challenge. The first one, I mentioned it before, like depending on where you are in the US and where you are in the world, the materials will be very different. So materials are very regional in concrete. Typically in concrete, you use only materials that are locally available. You can't transport them over large distances. So it needs to be done almost plant by plant. So we can't really have we can't really optimize concrete nationwide or anything like that. The concrete is made of materials that can change over time, like the aggregates, the cement, the flash, all of those things. Those are materials that have certain types of variation over time. So we need to take that into account when we make some prediction. We need to account for the viability of materials over time. That creates a challenge. There is another challenge that comes really from the numbers, right? So each plant, so there is several thousands of plants in the US, and each of those plants have in their catalog several hundreds of concrete, each of them having several certain strength requirements, certain slump requirements, etc. So it needs to be done at a very high throughput fashion if we really want to have an impact. Concrete is a material that is very variable, so it comes with many uncertainties. It's not just about the material that you are using. There is also like the type of truck that you are using, the type of plant that is used to make the concrete, the temperature. All of those things eventually affect the performance of concrete, so we need to take that into account as well. Then when it comes to concrete, there are some properties that producers care about, but are actually hard to quantify. So whether a concrete is pumpable or not, whether it's finishable or not, like those are properties where there is not like a very standard test, and yet those are important properties, but they don't really come with a clear number. So we need to incorporate those more qualitative estimation of concrete into those models. And then there is again the issue of the data that producers they don't necessarily have a good way to store their own data, and so that makes it hard to access those data and build those machine learning models. So the way we are addressing that is that we're trying to build like more like a software solution that can solve this at a much larger scale. So we call this Concrete AI. And the idea is really to build a software that's going to connect to the database the software that producers are using and directly optimize in an automated way and in a high throughput fashion their concrete using their material and their data. So it's more like a software solution that we are trying to develop. And so like the key idea of this is that we need to do that with as many partners as possible, because that's how we can get as much variety in terms of the materials that the machine learning models are exposed to. We need to, like, to some extent, much more important than the machine learning model themselves. We need to have some tools that can have access to the data. So we build some APIs to directly connect to the software that concrete producers are using to directly extract their data and use them to build the machine learning models. We develop like a high throughput optimization approach that can really do it not concrete by concrete, but directly can optimize all the concretes at a given plan all at once in a high throughput fashion. And we also move towards using active learning to really take into account how the performance of the materials in concrete are changing over time and to adapt dynamically the machine learning models accordingly. So just I want to finish by just showing you a couple of results that we got. So far, using this approach, we have already optimized about 2 million cubic yards of concrete. So this is still like very small as compared to the the national production of concrete, but that starts to be like a pretty large scale optimization, at least much larger scale than what we can do if we just work in the lab. As of now, like the result that we got is on average a 30% reduction in the carbon footprints. So clearly, it's not completely solving the carbon problem of concrete. There will need to be some other solutions, but this solution has the advantage of being directly accessible with what we have now, the materials that we have now, and the plants that we have now. So it's more like a low-hanging fruit that can help us reduce the emission tomorrow while we wait for other types of approach to really decrease even further the carbon footprint of concrete. Again, like one thing we noticed is that it doesn't come with any kind of cost premium, and that's really important in concrete. Like concrete is a commodity material, and especially maybe in the US and in Europe, people are willing to spend more to get some green concrete. But when it comes to developing countries or India, China, this is where most of the concrete is made, and we can't expect them to pay more for concrete, right? So, for example, when it comes to China, every 2 years, China is producing as much concrete as the US did during the entire 20th century. So this is where really most of the concrete is being made right now. And I mean, they start to care more about carbon footprint of concrete, but those developing countries, they have a need for infrastructure, and we can't expect them to really pay more, right? So this solution has the advantage that it's not increasing the cost of concrete. Most of the time, it's actually decreasing the cost. And just to give you an idea, like this is more like a blue sky number, but like that's the number that we estimated. Like if everybody was using AI to optimize their concrete in the world, then we would prevent about 500 million tons of CO2 from entering the atmosphere annually. So just to give you an idea, like this number is more than the annual emission of a large country like France. So it's really a pretty big opportunity. Again, it comes from the fact that we produce so much of concrete that any kind of iterative improvement that we can make to concrete is going to have like a very big impact. So yeah, so I'd like to stop here, take any question if there is any, and those are some reference if you want to know more about the machine learning model that we have been using, etc. So yeah, thank you so much for having me here.
Yeah, fantastic. Well, thank you very much. So one question is, you point out that in order to roll this out globally, you have to be sensitive to the local conditions. What would that take? I mean, how much do we know about the availability of the different inputs across the world?
Mm-hmm. Yeah, I mean, it's so just to give an idea, so far we have used this approach. So in the US, And already within the US, like the level of variation from California to Illinois to Virginia. So we have done several pilots in California, Illinois, Virginia, and Utah, and each of those markets is very different. So fly ash is very different. Sometimes it's available, sometimes it's not. The types of aggregates is very different. So even within the US, that's a significant challenge. And like there is no, I would say, like no mystery there. You just need to have enough data from each of those distinct materials. So it's hard to say for sure like how much data it would take to really have some kind of a universal model that could be applied anywhere in the world. So far, our approach has been to get local data and like build more specialized model for each region rather than trying to build like a generic model that would apply to everywhere in the world. I think it can be done at some point if we really have like a significantly larger data sets. So we also try to move to Canada. So we have a partner there, and again they have very different materials. So it's we need like a fair amount of data from there. We're also trying to explore South America, and India is the latest that we are looking into. So again, like very different materials. So I think that's really the main barrier so far, is that each country has its own material. So we need some brand new data every time. Like we can do some transfer learning, things like that, but we can't really directly apply a model that was trained in the US won't apply directly in India, and vice versa.
So this means that you need chemical tests of the new materials.
Yeah, but so this is typically not an issue because that's already something that is required. When you produce concrete, you need some certification for the material. So like the data should already be collected as per the building code. So it's really a matter of more accessing this data. Sometimes it can be just a bunch of PDF in a directory. So it's not organized. It's not, most of the time it's not really in a structured format. So the challenge is really about how do we access this data and turn it into something structured that can be used by the machine learning model.
Okay, and that's where maybe text models of some sort, because it's PDFs or OCR paper documents, that kind of thing. But
exactly, yeah.
Physical tests have to be done just for the local country's code.
Yeah, exactly, right. So at some point, yeah, using some kind of language model or even like some kind of OCR would be like so far that's something we have to do manually. So clearly that would be something that can be done at some point using maybe natural language processing, something like that.
Well, and the other thing is the techno-economics of it, the availability of the various materials. To what extent do you have to, do they exist databases of mines, and to what extent do you have to just go on the ground and figure it out?
Yeah, so far our approach has really been to use the material they have access already. Like we are not really suggesting new materials that they don't have at the plants already. I think that would be something very interesting, but as you say, it would require some technical analysis to compare the cost of bringing those new materials to the plant. So that's not something we are quite there yet. But like I think from what I can see, even with the materials that people already have today, there is already like a big opportunity, just for the fact that making concrete is like a fairly cumbersome process, and so there is many inefficiencies in the concrete that we are using now, just because if you want to change something into concrete, like you need to try, wait 28 days, see how the 28 days is typically the time at which we think, okay, it has been long enough, we can measure the strength of concrete. So if you want to do it without machine learning, basically that's what you have to do. Like you need to try something, wait 28 days, see if it gives you the expected result or not, and if not, do another cycle, wait another 28 days. So this is really something that is very hard, especially when you have like hundreds of different concrete at each plant. Like you can't test them, all of this like this, and optimize them one by one. So, and that's why we find that there is this this big opportunity to do this with machine learning, because it's just like those concrete, they have not been carefully optimized, just because it's so time consuming to do this. So to some extent, what the AI that we developed does is something that a human can do, but it would just take a very long time to do it concrete by concrete, and to wait every time 28 days and things like that. So, but yeah, I think you're right. I think the step one is to do with the materials that they are using now, and that's already like a big opportunity. But then the next step would be to look at opportunities of using all the materials that maybe they are not using now, maybe new types of chemicals, things like that. And like in the years to come, there's also going to be like more and more like alternative cements, new types of cements that people are working on. And so depending on the cost, depending on where they are produced, like it might make sense for certain producers to use that, while for others it won't make sense. So it's going to be a much more complex optimization problem, like to optimize this more as a supply chain rather than like what we are doing now, which is like more limited to the materials that they are using today.
Okay, so then when you go out to the manufacturers you've worked with so far, I mean, they clearly do not have the technical expertise yet to do this stuff. But in addition to that, you're ultimately offering them a cheaper product. Ignore carbon for a second, but a cheaper product that they can is more manufacturable and whatnot. When you give them a formulation, is that job done? Is it not profitable for them, or are there kind of organizational human barriers that make this process difficult?
Yeah, I mean, it's you're perfectly right. Like even though you would think that would make a lot of sense for them to capture those additional profits and reduce the carbon emission as well, like there is at the end of the day, those are made by humans, and there is some inertia from the producers themselves. Like they have been producing concrete in a certain way for many decades, and so changing, even though like the change that we prescribed are just like small change, using a little bit more of this, a little bit less of that. It doesn't require any change in the plant itself or things like that. But even that, it takes. I mean, they need to test the concrete and convince themselves that yes, it's feeling the same as the concrete they have been used to. And then there is from the other side, like the side of contractors, developers, things like that. Like they also have been used to certain types of concrete, and sometimes, I mean, of course, you have certain companies, like Google being one of those, that really have some clear targets on neutrality. So every time you build a new data center, like there is some targets on global warming potential and things like that. But most other companies don't have those targets in mind, and they have been using certain types of concrete products, and they are not very open to changes. Like when they have something they are used to, like it requires some convincing for them to switch to a new type of concrete, even though it's supposedly more economical and less carbon incentive. Like I think it's a common human thing that we are not necessarily very open to changes. So like the thing that are helping to some extent is there starts to be more and more targets on global warming potential of concrete. So there is the Inflation Reduction Act, for example, that gives some incentives into reducing the carbon footprint of concrete. In Europe, they start to have like this carbon tax, which really is a strong motivation to reducing the carbon footprint of concrete. Like unfortunately, we don't have this here. And then there's also the fact that the cost of the material is really increasing a lot. Like the cement is typically increasing at a rate of 5%. Like the cost of cement is increasing by 5% every year. So it means that on the other hand, the margin of the concrete producers are really decreasing over time, which also gives them more incentive to try to actually optimize their concrete a little bit more than what they have been doing traditionally. So there are some like motivation, like financial and environmental motivation, but it still remains a challenge for sure to change the way people make and sell concrete.
Right. So if you can make it slightly cheaper, or put in a different cost trajectory for all the actors, they will have a financial motivation to transition. It just takes time for all of them to switch and validate that the new design is both, is actually cost effective, that it's actually works with them for them.
Yeah. I mean, clearly again, concrete is so cheap that if you want a new types of green concrete to be adopted at a large scale, it needs to be at the very least cost competitive, and if possible cheaper. Like otherwise, it won't be adopted at all unless you have some kind of carbon tax or something like that. So that's really the only way for those types of approach to be used. They need to be economically viable.
Yeah, that makes sense. Well, fantastic. Yeah, thank you very much. It was fascinating and pretty valuable.
Well, thank you so much for having me.